Okay. Good. Very nice. Let's continue. And I was really happy that you asked questions during my last talk. So please keep on doing that. So now we will go through actually many things. What you can actually do with these basics that we just learned. We look at some real materials like TBG, and then also what can you see in the normal state above superconductivity in this flat band system, and transport, and finally something about many-body quantum metric. So this quantum metric that we have talked so far and will talk until this is a single particle property that you can just calculate from the non-interacting band structure. All right. So obviously, when these experiments came up, we started to think that, okay, does our theory apply here? So everybody here knows about twisted bilayer graphene. We take two graphene sheets, twist them with respect to each other, get flat bands, and then some correlated insulators and superconductors in the phase diagram. So we have this review where we specially discuss what would be the significance of quantum theory, quantum geometry in TBG. Okay, but these are my co-workers to our TBG work. So my student, postdoc, and Tero Heikkilä from Jyväskylä, his student. And here again, still this, I wanted to have one animation in my talk. It's of course not made by me, but still. So here you see, when you twist the Dirac cones of the two layers, they merge, and at some point you get this very nice flat band in twisted bilayer graphene. Right? So we wanted to look at these quantum geometry effects there. And it's not only us, obviously this was interesting for others too. So there were two other papers doing very similar things, all appeared about the same time. So if you want some quick to read review of this, there is a nice article by Laura Klassen about them. So in our works, because we knew that multiband effects are important, we thought that we have to take this other band seriously. At that time, like 2019 or something, when we started the work, people were very naively using this Pitziker-McDonald continuum model, or just taking 4 bands and other bands not interesting at all, and so on. We thought that, okay, let's have more bands, but there is a problem. So here you see how many bands you get when you increase the twist. Let's put this away. At the magic angle, you have like 12,000. And we want to do mean field theory of superconductivity. So even the mean field is very challenging if you have 12,000 bands or 12,000 orbitals. So we decided to use so-called renormalization Moir method, where you do some rescaling and keep the Moir periodicity and Dirac velocity invariant. And with that, we could reduce the number of bands to something like 700, and that's still doable in mean field calculation. It's a little bit tricky, but it's very doable. And since the pairing mechanism was not known and is still not known, we considered 2 variants. The S-wave superconductivity with on-site interaction. By the way, all my things that I presented last lecture were kind of assuming this, like that, this type of Hamiltonian. But of course, we are not related to, limited to that, and all this quantum geometry stuff, it also applies to other types of pairings. So we here consider also the nearest neighbor, or RVB type pairing, where the nearest neighbors pair, and this could come from electronic processes. Yes?
What's the roughly energy scale of 600 bands? Upper energy.
No, I mean, it's more like... yeah, I never thought about it, but it's way bigger than most people consider in these studies.
Why I ask you this question is that I think that for graphing model, you use the Dirac, actually you have a valid upper energy cutoff of 2 MeV,
Yeah.
and then are not allowed to use the VM model.
Yes, but this is not really, okay. This is really a lattice model, so this is not the BM continuum model. This is a real lattice model, assuming really the positions of the carbon atoms and some hoppings and some interlayer hoppings. So it's not a continuum model. Yeah, so these are the two types of interactions. And then we calculate the BKT temperature, so we evaluate the superfluid weight, and you see it gives the BKT temperature via this relation. And always we found that the local interaction, the S wave, is a bit bigger than the RVB. And as a function of filling, when the interaction is quite small, we find these domes that are there in the experiments, while for large interactions, they are gone. And furthermore, what we found that if we allow this non-S wave autoparameter, the autoparameter symmetry is quite complicated. We get some mixed SP and D symmetry and nematic superconductivity. But here comes the main message then. We wanted to analyze this quantum geometric contribution. So we can do it in our model. So the superfluid weight, we can divide it to the two contributions. And here you see them as function of the interaction. So the maximum gap is basically the interaction strength, which we don't know. And the pink area is the conventional one, because the TBG bands, they still have some dispersion. So you get completely conventional superfluid weight as well. But the blue area is the geometric one. So it does have a sizable influence. I mean, we don't know exactly where we are in this interaction axis, but based on the TC that the model produces, maybe somewhere here. So depending on the type of pairing, it might be very sizable. So also another thing is that we checked how many bands we need to include in this model to get convergence. So for instance, the result is here is completely different from the converged result. And here it's basically missing the geometric contribution. If you only take the 4 flat bands, this is quite obvious. Nowadays people have shown in many ways that there is quantum geometry coming from the upper bands, but here it's so. Okay, but now this was this TBG theory has developed really a lot, and I would not trust these calculations quantitatively at all, because they are much better theories. But I still think this qualitative message is clear, that you need to take into account quantum geometric effects in this system, at least in order to get the right numbers. I mean, there is some dispersion, so you will get something from there, but to get really as big effect as one can see, you need to take it into account. Okay, so then experimentalists also got interested in seeing whether these things are there. And this is a recent paper from last year. They did not measure the superfluid weight because it's a bit tricky, but they measured the critical field, which gives you coherence length, and also the critical current. And there are usual BCS relations for this, which then give you an estimate of the superfluid weight. And this is plotted here. So this red line is the extracted superfluid weight from these measured quantities. And this line here is, from maybe you remember from the beginning of my first lecture, that I was saying what the naive BCS theory that you get from Landau and Lipschitz gives is this density of particles divided by effective mass of the electron. And it's completely off. It would be like this. So clearly that cannot tell you what happens. And then these authors, they just made some kind of dimensional analysis. They looked like the gap and some numbers, ad hoc numbers, and this gives much better match. So this is saying that maybe this rather has something to do with the gap. And I remember the isolated flat band result maybe that I showed you. We have this proportionality to the square of the gap plus the quantum geometry thing. So this is an indication that quantum geometry could perhaps play a role in TPG. But yeah, this is not like yet some kind of smoking gun proof. And there is a nice review by Carlo Penacker about this paper if you're interested. Now there is another work which is very, very recent, just in archive, a couple of months ago. There they were able to measure the superfluid weight directly in TPG. So how you basically how you measure is kinetic inductance. And you can use some RF circuits, and if you bring them close to your TPG material, the resonances shift, and this shift gives you kinetic inductance. And then that gives superfluid weight, because superfluid weight is actually inversely proportional to kinetic inductance. So this is like a direct measurement you see here. Here is kinetic inductance, here is the superfluid weight. And you see the results look similar to this deduced one. And they do it for pole electron and hole dope. And again, here is the single band PCS result, completely useless. And I remind that the quantum geometric theory gives something that is proportional to the square of gap. And this could, of course, give this kind of domes, because those are like the superconducting domes, very much related to how the gap behaves in these systems. So this is already much better, much stronger evidence. But to me, this is not yet the final evidence, because what I would like to have is really microscopic and strong and great theory of TPG from where you can calculate the DS and not just use them as kind of simplified formulas, but really numbers vary some parameter and then match to the experiment and so on. So hopefully this kind of stuff is coming. Right. So that was about the real material, and now we go back to model systems where we can learn generic things. So I have said a lot about these results, analytical results that were obtained for isolated flat bands under various kind of simplifying conditions. I mean, it would be nice to use them also for systems that are not so ideal. So we wanted to see how good those results actually are by comparing to beyond mean field calculations. And further, we wanted to study the temperature dependence, which is not yet looked very much. So these are the people in this work. So Reko is actually there in the audience. Yeah, he's my PhD student, and Kukka is a former PhD student. You know, she was the key person in this orbital position stuff. Now she's at ETH Zurich. Right. So in this work, we consider bipartite flat bands. So whenever you have a bipartite lattice, there are some nice result in this paper but let me first remind what is bipartite. I think it was told yesterday already once, but it's a lattice where one type of orbital, let's say here this A, is connected only to the other type of orbital. Like here the other type is this C and B. So you see it's a bipartite one. So the result tells that in that type of bipartite lattices, you will always have flat bands. And how many? Well, number of orbitals in the bigger sublattice minus in the lower number of the orbitals in the smaller sublattice. So in the Lie lattice, it's 2 minus 1, 1 flat band. You see here. So we consider this kind of lattices because it's nice to change the ratios, I mean, how many flat bands you have and so on. And look at the isolated flat band results, which now come for the millionth time here. So here's the quantum metric stuff. Here we have number of flat bands divided by number of orbitals. So in order to test, for instance, the validity of this, we wanted to vary how many orbitals we have, how many flat bands. And you can do this within the Lie lattice context, for example, in this way that you add one connection. So I call it connected when I don't have anything here, it's just connected. When there's one orbital, it's called extended. And if I put 2 orbitals here, twice extended. And number of flat bands, number of orbitals in the flat band subspace, and this is the number of flat bands. So you see one of these, this extended one, has a different ratio for this. So let's see whether it matters. But in this work, we also wanted to go beyond mean field to test these formulas in a better way. We used dynamical mean field theory, where you have a lattice system and you isolate some point, maybe one lattice site or some cluster, and you solve that subsystem exactly, like quantum Monte Carlo, for instance. And you include at that point the rest of the lattice as some kind of effective mean field. And then that goes to your impurity solver, and you get an exact Green's function, like this. From the exact Green's function, you extract the local self-energy, you plug it in and calculate with that the whole lattice Green's function, and there you get the effective field and so on, and you do it until everything converges. And for instance, in this system, we took a cluster that has one unit typically. Then from this method, we can get the superfluid weight, and it looks almost trivial how you did. You just have this relation for current. Current you can evaluate in this system. You have the ground state now, and you evaluate the current operator. And you just first plug in the vector potential in this way. You change hoppings, so it's like this thing. And then you see how much current you have. And you know what is A, so you get D from there. It actually works. So here are the this determinant of the superfluid weight, which is in 2D, you have to take a determinant as function of temperature. And indeed, you see that this extended version, which had the biggest flat band to orbital ratio, it wins. It has the highest TC, as we expect. So then we went to see, okay, let's now fix this flat band orbital to flat band ratio, and then vary something else, vary maybe the quantum geometry part. So here we took different extended Lie lattices, decorated, diagonal, and x-directional, and we can also make some of them gapped by changing these hoppings a little bit. So at the case where all the hoppings are the same, they look like this. So this is usually Lie lattice, and then for this we have a bit different band structures. So now I want to have some kind of quiz that, based on the knowledge that you have so far, or whatever intuition, look at these. They have the same flat band, so orbital to flat band ratio. So that doesn't help you to determine which one would have the highest TC. But maybe the band structure tells something, so I will make a vote. That you should decide what you think will give the biggest TC. So I leave this out because obviously this is just for comparison. So the diagonal, who votes for this? Okay. And who votes for x directional? And decorate it? Okay, it seems this was most popular, and then this and this. Yeah, and then let's open a gap and then ask again. So who votes for this one? All right, and this? No, yeah, well, and this? It seems that you don't believe they superconduct. I see so many people who don't vote for anything. Eh? All right. But you have learned that the quantum metric is important, so let's now do the vote again. So here I plot also the quantum metric. It's in the color scale, so this yellow is good. So now, and this is a very small gap here. So who votes for this? What about this? Okay, a lot of hands. What about that? Nobody. And then we open the gap and it looks like this. So who votes for this one? This one? And this? Yeah. Of course, this was easy for anybody sitting behind Rekov. I saw that he was voting for his own result. You voted right. Okay, so let's see the result. So in this case where we have a small gap, it is indeed this x directional that wins. So you were, many of you were right. There is a lot of quantum geometry here because there is a band touching, and it's best here. So here is a function of delta, so this is this case. And these green lines are the biggest. This is a bit more tricky. All of them seem to have kind of a lot of quantum geometry. And here, it's actually this diagonal one that wins. Look, at this point. So it has quite some quantum geometry, even when these bands are so far away. And by the way, here is one very important message. So a lot of things in superconductivity research has been done like that. Okay, we have our band of interest. I'm not talking about flat bands now, but there is some kind of relatively isolated band. Then there are other bands away. And now my interaction scale is so small that it's much smaller than the distance to other bands. For instance, look at here, these are in the scale of hopping. So this is like twice your hopping would be big energy scale. So you could think that in some band, interaction is small. And then the step from there is, okay, let's make a single band Hubbard model, and that will describe our system. Now, that's of course completely wrong in this sense, because when you go to the single band model, you might miss all the quantum geometry effects on the transport. So even if your interaction is like a small scale compared to the distance to the next band, this quantum geometry that you get from the other bands can be big, and it can be important for transport, like superconductivity. It could be important for electron-phone coupling and so on. So this quantum geometry gives like another reason why we should worry about other bands. It's not only whether our interactions couple to those. So, so now that this was the quiz, so this wins. I will come back to this. But also another remarkable thing here is that this is our simple formula calculated for isolated flat band, zero temperature, and yeah, that's basically uniform pairing. So a lot of assumptions, and of course these calculations are also zero temperature. But anyway, they don't assume isolated flat bands. I mean, there can be band touchings, no problem. And also, not all of them have uniform pairing, and they still and it's beyond mean field. I mean, this is mean field. These are now dynamical mean field theory. These solid lines are this formula, and they pretty much describe what happens. So at low temperatures, actually, this is a good rule of thumb. Yeah, so here I wanted to show also like why this, this diagonal one could win over this, even when there is a bit of quite big quantum geometry here. If you look, the whole Brillouin zone, it's quite spread there. And in this formula here, you have to integrate the quantum metric over the whole Brillouin zone. So it can be a big number. All right, so this was about low temperatures. Then we wanted to see also the finite temperature behavior. And for all these variants, we calculated the superfluid weight as function of temperature. And here you see it. And quite interestingly, all these different lattices seem to collapse on some kind of power law behavior, T to the fourth. So in a simple BCS theory, in low temperatures, you have certainly something not a power law, and in higher temperatures, it can be certain power law. But here, the whole behavior seems to be captured by this T to phi behavior. And why this? At least we can explain it by one step. So here you see the gap in different cases, and that one in this p orbital, it follows square root of T to the 5. And according to this relation, the simple formula, the superfluid weight is square of the gap. And here it seems to be really matching very, very well, even if these are finite temperature, dynamical mean field theory, and so on. Why here we seem to have this power 5, I don't know. That's a mystery. And of course, one should be always a little bit cautious with power laws, but I can kind of visually here, it looks like 5, but we have to look at it further. But anyway, this kind of power law dependence of a superfluid weight could be one way for experimentalists to see these flat band specific effects.
Sorry.
Yep.
Why is the x-dimensional extension are different from that?
Yeah, okay, good that I forgot to mention. This deviates clearly, so it doesn't. And in that one, I don't know, what is this 599?
I don't know.
Yeah, it's a typo. Yes, okay, but it's just this x-directional, and there we are quite far away from this uniform pairing condition. So the order parameters at different orbitals are very different, so we suspect that we should actually consider some kind of average of the orbitals or something like this. The others are either strictly uniform pairing or closer to it. Good. So that was the latest work about superconductivity, and let's then go to the normal state. That can be very interesting also. So basically I tell very briefly about these three works. And let's start with this. So here we thought that, okay, let's forget about superconductivity, just look at flat band systems with attractive interactions. And you can be in the normal state. And we looked at some very nice model systems, like for instance the Kreutz ladder, which is semi-1D. And then we can put the flux through. So this is like a Haronov-Bohm effect. And then we can calculate what is the properties of the energy of this system, basically the interacting state energy. And we can get this exactly from DMRT, for instance. we calculated, and we saw that when we have flat bands in this system, it has a period of pi. So here this flux is 2 pi. So it's this divided by 2, so it's pi periodic. So this means that your charge carriers have to have 2 charges. And then when we are not in the flat band, the period is 2 pi, means the charge carrier is 1. So we could show that always, no matter it's flat band or, superconductor or normal state, in this type of flat bands, the charge carriers have always charge 2e. So they are Cooper pairs. Only Cooper pairs can move, and they are the only things that can move also in the normal state. And in this system, it's related to local conserved quantities of this geometry. So this result is not general in the sense that it would happen everywhere, but it happens in certain lattice models with certain properties. So that's quite interesting. So this tells, and in some systems you would really have like a pseudo gap, kind of almost perfect pseudo gap above TC, where only pairs can move. And then another normal state study. So here we look at non-Fermi liquids behavior in a repulsive Hubbard model in a flat band, and look at the double occupancy, which actually in ultra-cold gases is a quantity that they can measure. Maybe it's not so relevant here. I just say that in a usual band, the temperature dependence of that quantity would be like this. But here in the flat band, it goes totally other way, and that's an effect of, signature of non-Fermi liquid. But here I talk more about these non-Fermi liquid features. So we looked at, again, the Lieb lattice, but in the attractive interaction. And we wanted to have access to the above TC quantities, like maybe pseudo gap and so on. So we did, again, a DMFT study with the cluster of the unit cell of the Lieb lattice, this Hubbard Hamiltonian. And for instance, to see whether there is pseudo gap, we should evaluate the spin susceptibility, or pairing susceptibility, never mind. And this requires in the DMFT evaluating 4-point correlators and then calculating them with Bethe-Salpeter equations. And here is the result. As function of temperature, this susceptibility, you can see that in the A and C sites that correspond to the flat band, it really goes down. In the B side, which is not the flat band state, it goes up. So spin susceptibility is very much suppressed in low temperature, so this means there might be a pseudo gap. By the way, the nice thing about Lieb lattice, why we love it, is that there really 2 sides correspond to the flat band. In some other systems it might be like a mixture of orbitals, but here these 2 correspond to the flat band. You only need to look at then what happens on those sides, and you know the flat band behavior. Now, okay, of course, ideally, I would like to see a gap in the, or pseudo gap in the density of states. However, the spectral function is annoying to get from DMFT because you need to do analytical continuation. So we did use this kind of approximation that you actually get it from the Green's function, and it approximates this spectral function. And from that, we see that when we increase interactions, indeed, there seems to be something like a gap forming here. So in this Lieb lattice above TC, there seems to be a pseudo gap for large enough interactions. And this is not only our work, some other people have predicted it as well. And then we looked at the small interactions, and there we found something that nobody else has pointed out. So we looked at the quasi-particle weight, basically, or the imaginary part of the self-energy. And if the system has insulating behavior, then this imaginary part of self-energy should diverge at the 0 Matsubara frequency. And we see that behavior when we decrease the interaction. This is a very low temperature, beta is inverse temperature. So there seems to be like an insulator coming. Now this is interesting because if you think about flat band and no interactions, it's insulated by definition. Okay, fine. Then if you add even a small interaction, I have told you that you get immediately this interaction-induced movement of pairs or something. So why do we kind of have an insulator-looking thing here in an interacting system? Well, we think that since we have a finite temperature, it might be that the interaction is not enough to really make pairs. And indeed, we looked at the gap and it doesn't appear there and so on. So, sorry, no, I should not talk about gap, but yeah, basically it's plausible that for very small interactions you don't get this pseudo gap. So then you are kind of seeing the initial insulator. So it's very different type of insulator from, for instance, in Mott insulator, which is caused by strong interaction. This is kind of that interactions are too small to do anything due to temperature, and then you see the underlying insulating flat band. And the temperature dependence of this quantity goes very differently from Mott insulator. Okay, so everything that I have talked so far is about equilibrium, because in a superconductor, even supercurrent is an equilibrium, ground state property. But in real world, of course, you make a lot of devices out of superconductors. And then there is interesting questions, what happens in non-equilibrium. For instance, if you have your superconducting material and you impose voltage over it, this is non-equilibrium. And we studied it in this paper. And again, it's a completely different story for flat bands from the usual dispersive one. So we used there this type of model system, toy model system, I would say. I will soon show why this sawtooth ladder is nice. So this would mimic our flat band superconductor or flat band system. And then the leads that you connect to this are modeled by just some big superconductors, very usual ones. And here the sawtooth ladder is nice. In an infinite sawtooth ladder, you have one flat band and one dispersive band. So you can easily compare them. You can have like a gate potential that puts the Fermi energy to one of them. In a ladder, which is finite, of course you don't have bands, but you still have discrete states that kind of mimic these continuum, large system bands. So you have kind of flat band states that are completely localized. If you put your electron there, it doesn't move anywhere. Also the edge states, now it's finite, they are localized. So these correspond to a flat band. But then there are dispersive states which have enough occupation and all orbitals so that current could just go through. And then we do a non-equilibrium treatment of this. So it still looks like a mean field theory of superconductivity, and it is, but everything is time dependent. Even the Hartree fields here and the order parameter and so on. And then to solve this thing self-consistently, we used the Dyson equation and solved the Kadanoff-Boehm kinetic equation. And this gives our Green's function for each frequency. So it's very easy to look at some certain type of, let's say, Josephson effect or something by looking at the corresponding frequency. And now let's have a look.
Sorry.
Yeah.
In the system, there is time periodicity, or you're not considering
Well, at this level, not. It's just the general omega. But of course, it's known that if you have a Josephson effect, for instance, two superconductors can connect them by a voltage difference, then the AC Josephson effect has a period that is given by the voltage difference. But these ones, they don't have any periodicity that you plug in. But here it indeed comes. So now we have a constant voltage bias between these. We can vary the gate potential to be at the different bands, and then we evaluate the current by looking at some certain point and where the particles move. And here are the results. Now, this is the gate potential that we use to be at the flat band or at the dispersive bands, and there are different situations. So we can pick the 0 omega, that's the DC case, and then AC is this voltage, omega 2 times voltage, and have interactions or not. In the dispersive states, I mean, it doesn't matter much what condition you have. The current just goes through. However, in the flat band, everything else is 0 except the AC interacting case, and that's the supercurrent. So obviously when U equals 0, when you have a flat band, nothing should go through, it's fine. But even the DC current in presence of interactions doesn't go. And that was a bit surprising because in this setting where you have voltage difference, the DC current is given by multiple Andreev reflections. And that's a coherent process involving pairs on both sides. So one might think that it would occur here. But it does have as part a movement of individual quasi-particles. And now in a flat band, single particles don't want to move. So apparently that's such a strict requirement that even in this type of non-equilibrium system, the quasi-particles simply don't move, and you don't see DC current. Right, and then, sorry, I should have emphasized this was for the superconductor junction. Now you can put one of the leads or both to be normal, and then we don't see anything in the flat band, no current. So you really need to, only thing that goes through is the supercurrent. So, and quasi-particle transport seems to be quenched. So this tells that it's not only that this flat band stuff can help you maybe get a higher TC or something, but it can give different qualitative behavior of your devices if the quasi-particles don't move so much as they do normally. And in some sense, this is the carrier. Flat band superconductor is the carrier of the pure supercurrent. Maybe kind of like the best superconductor ever. Right, so these quasi-particles are annoying in some contexts, so maybe we could have some help for that. Right, before, this was not even my contents, but I would like to mention if there are any people who are interested in bosons and Bose-Einstein condensates, we have shown that quantum geometry plays a role there as well. But now I just want to say briefly something about two topics. And this DC conductivity, now let's forget about superconductivity. This has nothing to do with it. Just usual DC conductivity, this kind of things that are taught to you in the elementary school, that current goes through some wire. And this is work by Kukka. So if you want to describe just the usual DC current, You can do it, for instance, with semi-classical Boltzmann theory. And this is the formula. Here you see there are two derivatives of the dispersion, nothing else. So this formula gives you 0 at the flat band. So it's a saying no current in a flat band. However, this is an approximation. So if you want to do a bit better, you can take the Kubo-Greenwood formula, which looks like this. And here, you have the current operator that we had in superfluid density, which is current-current correlator. So, and it has these multiband effects here, derivatives of Bloch functions, so maybe quantum geometry comes out. I think many people got interested in this, and they were saying that there is some quantum geometry there, but we thought that it cannot be so. Because they claimed that there will be a current, DC current in the flat band, and that's proportional to quantum metric. And we knew, of course, our SSH model where you can make it disconnected, you still have finite quantum metric, it cannot be true. So we started to look at it. And by the way, here, this eta is some kind of finite scattering rate that people use to derive these formulas. They would describe some scattering from the impurities that gives you resistance and so on. But in the end, you take this to be something very small. So let's see what really happens. So those people who predicted that there is quantum geometry dependence, they didn't use this Kubo-Greenwood. They used the Streda formula, which these two formulas in many contexts produce exactly the same results, and this is thought of being a very good one as well. So it's given by Green's functions. And there, if you take this limit of the scattering rate going to 0, after taking the 0 temperature limit, indeed you get the quantum metric dependence, but that's only because there are some ill-defined terms at the Fermi energy. So normal, I mean, the ill-defined terms are there, but normally if you have a dispersion, your Fermi energy in this integral is just 1 point. So it doesn't matter. Now if you have a flat band or even a flat portion, you will have something ill-defined here that you integrate over a finite set of energies, and this causes problems. So actually you cannot use this formula. It's just wrong in the flat band context. That here is an example. Again, the sawtooth, I don't know why it's not, it's now tilted, it's a different student. But anyway, it's the same thing that we considered in this non-equilibrium stuff. And here, this Streda formula for different scatterings, it indeed gives you some 0 temperature, very high conductivity. And, but then the Kubo-Greenwood doesn't give, it just goes there. And actually, for this finite theta, you get something, but this is like the tail of the conductivity peak, of the AC conductivity peak at the band gap to the next band. So basically, there is no quantum geometry dependence there. It's just an artifact of this formula, and the problem came because we don't have a Fermi surface. We have like a flat set of energies. So this is just a general note to you that you should be very cautious when you do flat band work, because many of the formulas that are in the literature have assumed a Fermi surface, and now if you don't have it, you have to redo certain things. Good. So then the last topic, and this is done by my former postdoc Grazia, and Tomoki Osawa from Japan was also working there. And now you can, of course, define the quantum geometric tensor and quantum metric for a many-body state. So I have so far talked only about the single particle quantum metric. And by the way, I think it's really nice that we can have superconductivity related results that are based on single particle quantum metric, because that one you can easily calculate. However, it might be interesting to look at the many-body version as well. So now it's the same definition, just now this phi 0 is the ground state of a many-body system that you hope that you could solve, but of course you cannot, except maybe with Monte Carlo, but in general not. But you can always write it down. And this is, by the way, just another formulation of both the single particle and many particle. You can write like this. This is just a Hellman-Feynman theorem thing. Anyway, we will use here this. So look at this. It's like derivative of the Hamiltonian instead of the wave function divided by energy squared. And this phi here is now something very generic. We have not specified it. It's just some parameter. But let's make it more concrete. We at still this point consider very general Hamiltonian, which would have some kinetic part, some potential energy and interaction energy. And this kinetic part is like this. And then you can calculate the Drude weight. The Drude weight is in gapped system is the same as a superfluid weight, but in gapless system it's Drude weight. Maybe you have heard about it. And it can be given if you have a periodic boundary conditions and put the flux in. So then it's the derivative with the flux quantity of the evaluated at zero flux. And this is the length of the system. And we put such a flux in by putting it into the kinetic energy. Then we do, so here we have exponential of the flux, but we do perturbation theory. We evaluate the exponential only to the second order and write the Hamiltonian there. Then you will have this kind of perturbation Hamiltonian, phi and phi squared. And then we evaluate the derivative by in this kind of like, it's usual definition of derivative. And this will be the result. So this is, by the way, the current rate. We have something like this, the expectation value of kinetic energy. This is what you would think about Drude weight. It tells whether things move. But there is another contribution here, this kind of thing. And in general, there is no direct relation to quantum geometry, but we can show that if the many-body spectrum is gapped by some gap E, then this will be always bigger than equal than the quantum metric times the gap. And you see, this is usually positive. This is positive, so now the quantum metric makes Drude weight smaller. So this is a totally different thing than the single particle result. In the single particle result, if you have a big quantum metric, it's good. But there the meaning of that was different because it told about one-year function overlaps. Here it's more like that this is telling that maybe your many-body state is not so robust for these fluxes. And that would be told by the quantum metric when there is big distance between the quantum state is kind of bad, so it decreases. But this is a very general result, works for fermions and bosons and in various dimensions. Good, so I already told in last lecture that we have this new Simons collaboration. There are postdoc positions coming, these are the people, and you may discuss with me if you want. And by the way, in this consortium, we want to combine machine learning to a lot of other theory to find new superconductors at higher and higher temperatures and so on. Miguel Marquez is our machine learning expert. So when I was thinking, like I was preparing the talk to the interview at Simons Foundation, I thought that we should have a nice picture, and it could be something like a levitating thing. But then I thought that I would never ever ask my students, many of them are here, to spend a day or week with Blender to produce something like this. I thought that it's more fitting that I ask DALL-E, the AI, to produce, and it produced actually this like in 40 seconds, but not exactly 40 seconds. I had to spend a little bit of time with it, because in the beginning I just told to it that make a picture of the Holy Grail. I mean, the Holy Grail is the room temperature superconductor. Make the Holy Grail like from Indiana Jones and make it levitating, like our superconducting magnet, and so on and so on. And this is what I got. So there is still some work for us humans, but maybe by cooperation we will get there. So this is the summary, and outlook is obvious, and I hope to deliver this message that you have to look at the structure of the Bloch functions as well. It's not only the band structure, it's also the Bloch functions. Yeah, thank you.
Thank you for the nice talk. So, in the DC conductivity, for the calculations, you said that the Kubo-Bastin formula gives a problem for the flat bands due to the Fermi surface, right?
Yeah, so basically in the Streda formula there is a problem that comes at the Fermi surface, and this Kubo formula doesn't have it.
Okay, but the Streda formula is basically a surface and C contribution, right? Or no, there's two contributions from the Fermi C and the Fermi surface.
I mean, it's like this. So here you integrate over all energies, so above and below and at the Fermi surface. Then when you look at this formula, and it behaves very pathologically exactly at the Fermi surface, because certain energies, certain things go to zero then.
Yeah.
So for instance, it will start to depend on, there are various these etas, in which way you bring them to zero and so on. So it's very pathological right at that point. That leads to problems.
Yeah. But the previous formula doesn't account for possible broadening in the quasi-particles, right? The other formula.
This one?
Yeah.
Yeah, this doesn't have the same problem.
Okay, but does it account for the broadening of the quasi-particle? If the quasi-particle is broadened, can you see it through this formula?
I mean, this is formula for DC conductivity, so you just have quasi-particles without any broadening, and then you plug in all scattering effects kind of phenomenologically with this kind of scattering rate that you in the end put to zero. So I don't know, probably one could do this same stuff for when you have broadened quasi-particles. If you start from the initial Green's functions, probably you get something somewhere, but it's not visible in this one, this version.
Okay, thank you.
So I have a question about basically the same thing. So is the conclusion that there is nothing interesting with flat bands in a normal material, or?
Well, yeah, I would say that at least the basic DC conductivity in presence, when you don't have any interactions or correlations and so on, would be boring.
And the reason I assume is that, as you said before, in a flat band, it's only pairs of electrons that can move and not individual electrons.
Yeah, yeah. So it's basically the definition of the flat band that individual electrons don't move. Of course, in the AC conductivity, that's a different thing. There, you know, by interband effects, you can have AC, but the DC is really boring.
Right. I mean, but if you had, for example, say two flat bands and some interaction between them, so do you imagine that in the DC conductivity there is some kind of pairing mechanism which could allow transport?
Probably, like in effect, you will get then maybe non-flat bands if you have two flat bands with a coupling. So maybe.
Right. Okay.
Yeah.
Okay. Thank you.
Sorry, I have a follow-up. So this is the linear conductivity, right? If you look at the non-linear conductivity, is it possible that the quantum geometry gives some more contribution through the quantum?
Yes. Yeah, this is certainly possible. And in this kind of non-linear transport properties, people have studied quantum geometry a lot.
Hello, thank you for the nice talk. I got a quick question about the many-body calculation for the root weight. Yeah, basically the result was like there was two terms that, with opposite signs. And yeah, you were saying how in this case, like the many-body contribution actually works to reduce the root weight. So I'm just wondering, could that expression go negative if that second term dominates, or is it bound, that geometric term bounded in some way so that it can't become that large in the negative?
Yeah, I mean, that's a very interesting question, because in superconductivity, if you calculate superfluid weight and you get a negative one, of course it's physically meaningless, but it actually hints to you that maybe you have some other type of ansatz that you initially plugged in. For instance, it can be a signature of a pair density wave in superconductivity. So I don't know, maybe in same sense, if you get negative through the weight, of course, as such, it's not physically meaningful, but maybe it could hint that, I don't know, actually, if you kind of calculate your many-body state in some kind of approximate way, for instance, and then you get negative one, then that would hint that maybe your way of calculating the many-body state is not correct, that it's a different thing. But I guess that if you really exactly evaluate your psi zero, then this should remain zero or positive, because it's the physically meaningful one.
Okay, yeah, that's interesting. So, quick follow-up. So by that reasoning, then if you get a negative wave from the second term, that probably hints that the problem with your ansatz has to do, in particular, with the quantum geometric, or the quantum geometry of the state, right? Because that's what.
I mean, this one is by definition positive, but the whole thing could maybe at some case go negative.
Yeah.
Yeah.
Thank you.